Hi guys, here's a really quick recap of resonance structures to make sure that everyone really understands it. So what's happening is that you have electrons that are being shared in more than one electron cloud. And so they're moving back and forth between these different electron clouds so that all the atoms has as much stability as possible. And so we end up with averaging all the events that are occurring. So here we see in ozone between oxygen 1 and oxygen 2, we have a double bond in picture number 1, and between oxygen 2 and oxygen 3, we have a single bond. But in picture number 2, that double bond, those electrons have flipped over to a different electron cloud between oxygen 2 and oxygen 3. And so the double bond is now over there, and the single bond is between oxygen 1 and oxygen 2. Neither one of these things occur at a specific time. Actually, what's happening is the average is occurring because this flip-flopping is occurring so quickly that it actually works out that the bonds between oxygen 1 and oxygen 2 and oxygen 2 and oxygen 3 are an average of a single and a double bond, both in length, strength, and polarity. So we see here over with our resonance hybrid structure, we are showing the double bond as dashed because it's an average amount of that time. So our length here, if a single bond was a length of 2 angstroms and a double bond was a length of 1 angstrom, then our hybrid structure has a bond length of 1.5. And it has an average of 1.5 bonds between them. And the oxygen 1 and oxygen 2 are going to be partially negative because half the time they are negative and half the time they are not. And oxygen number 2 is going to be positive all of the time. So let's go to our next slide. And just remember that here we go. I'm going to change my color. All right. So when we go to draw, I have my little tablet here. When we go to draw this structure, right? So if we're drawing resonance structures, we're going to do this. And now this oxygen up here is going to have the single bond, and this oxygen down here is going to have, got those guys, the double bond. And so our resonant hybrid structure is going to be with dashes. And we're going to do a sigma there to show our partial negative charge. And our carbon right there. All right, so there we go for that guy. Let's move forward. So here on this slide, we see all our resonance structures for carbonate. And here we actually are showing how we average the charge on all of those oxygens, and we average the bond lengths, and we can do that either as a fraction or as a decimal. So on this slide, we're seeing how hydrogen is not going to share an electron there. It's not going to be part of this resonance structure as far as sharing an electron in its cloud because it does not need an additional electron to be stable. It is stable with that single bond, but those oxygens are going to share that electron. And we see here that we have an average bond length that falls between a double and a single bond between carbon and oxygen. Looking at the resonance structure of a benzene ring, C6H6, which is also known as an aromatic. And it's where we have 6 carbon atoms that are bonded together to form a ring. For them to be stable, they need to share electrons in a cloud, and it actually ends up being sort of where the electrons are just flowing around in this circle. And so organic chemists will actually show this flip-flopping or alternating of double and single bonds that we see in the top picture, structures 1 and structure 2. They will actually show, draw that as a circle, as we see in the lower picture. The center diagram there is how an organic chemist would actually draw this hybrid structure. So if you look at the picture on the top right hand corner there, we have our resonance hybrid structure. And so we see when we hybridize these 3 double bonds and 3 single bonds, the average is actually 6 1.5 bonds. So we don't have technically an average. We don't have 3 double and 3 single in the average resonance structure. What's happening is we have 6 1.5 bonds. And so we can see here when we take the bond length of a single bond between 2 carbons and the bond length of a double bond between 2 carbons, when we actually measure a benzene ring, we're going to see all of the bonds between all 6 carbons are an average between a single and a double bond in length and in strength. Very quick recap about formal charge. Formal charge is really important because it tells us what structures are actually going to exist in nature. When we take valence electrons and atoms, we can rearrange those valence electrons in a lot of different configurations. And so we need to figure out which of those structures are actually the most stable for the atoms, how they're going to actually fit together to be the happiest. And so we do this through formal charge. The formal equation for formal charge is that we take the number of valence electrons that go around any one atom, and we subtract the sum of the non-binding or bonding electrons around that atom with the bonding electrons that are around that atom divided in half. So we see that formal equation up top there in black. But the easy way to think about this is to look at any one atom, take the valence electrons, and subtract the sum of the dots and the lines. That's the easiest way to think about it. So here in oxygen, oxygen has 6 valence electrons, and when we look around this oxygen, we see 2 lines plus 4 dots, so 6 minus 6 equals 0. And so the formal charge of this oxygen on the left here in carbon dioxide is 0. Now, applying formal charge to figure out the most favored structure is pretty easy. There's a hierarchy. The first thing you want to do is figure out the formal charge for each of the atoms involved in the structure. Next, you want to see which structure has the most formal charges that equal 0. And so in this comparison, we see that the one on the left has the most atoms that have a formal charge of 0. So that's already telling us how stable it is. If we have 2 that are similar, then we want to make sure that the charges combined, the sum of all the charges equal the charge on the species. So we see here that we have a -1 anion. We want to make sure that the formal charges add up to equal the charge on the entire species. So here we have a -1, and we see that this species is -1. And then our last stop, if we're still having some structures we're trying to decide between, is that we want to make sure that the negative charges are on the most electronegative atom in our structure. And that just makes sense because they're going to pull the electrons towards them more than the less electronegative atoms in the species.